Hello AP Stat students. Today's lesson is on the standard normal distribution. We're going to find out how we can use those z-scores to help us when we have a unimodal symmetric distribution, or the bell-shaped curve. So first, we're going to start off with standardized scores. A standardized score for a particular data value is calculated by the equation on the right, x minus the mean divided by the standard deviation. It measures the number of standard deviations a data value falls above or below the mean, and we call this a z-score. So one example of a standardized score is a z-score. A z-score measures how many standard deviations a data value is from the mean in a normal distribution. The standard normal distribution is the distribution of z-scores, where the mean is 0 and the standard deviation is 1. This coincides with the empirical rule that we learned a couple lessons ago, in that if you go one standard deviation either side of the mean, we know that that's 68%. And if we go 2 standard deviations, we know that's 95. And if we go 3, we know that's 99.7. Okay. Well, using standardized scores, we can find percentages that don't fall exactly on 1, 2, or 3 standard deviation units above or below the mean. Okay. So the standard normal distribution has a mean of 0, standard deviation of 1, and we denote it as a capital N for a normal distribution, and then 0 is the mean, 1 is the standard deviation. So we already know some things about this distribution. We know that from the 68, 95, 99.7 rule, or empirical rule, that 68% falls within 1 standard deviation on the graph above. Okay. The empirical rule is a great way of finding percentages under a standard normal curve, as long as you're interested in a multiple of the standard deviation. But what do you do if your data point is not exactly a multiple? Like, what if your z-score was 1.5? Okay. So let's say you wanted to know how much of this distribution was less than a z-score of 1.5. Now, on the picture up here, that would put us in between 1 and 2. And I want to know what is to the left of that. So it's shade into the left. Well, I can't use the empirical rule because it's not exactly on 1, 2, or 3 standard deviations. So then we need technology for help. So we're going to use what's called the standard normal table. On the next slide, you'll see what this looks like. So here's the standard normal table. You'll notice at the top there's a graph of a bell-shaped curve, and then there's a z-score and some shading. The shading corresponds to these percentages that are in the table. Okay, so all I need to do is look up my z-score and then find it in this table, and that tells me what percent that shaded area is. So a z of 1.5 would put a 1.5 here, and then I need to find it on the table. And the way this table is arranged, the z-score is across the top and it's down the side. Okay, and so what we do is we go down the side of the table until we find the first 2 digits of the z-score. So that would be 1.5, that's right here. And then the third digit of the z-score is a 0, because 1.5 is 0. So I move to the top row where the last number is a 0. I trace down and across from those 2 spots, and where they overlap, that is the percentage. So this gray area up here would be 0.9332. And we usually round these percentages to 4 decimal places. Okay? But this is the same as 93.32%, because we'd move the decimal 2 places. Okay, but most of the time we will write your answer in this format. Okay? Here's another question. It says, let's find the area to the left of a z-score of negative 1.28. When your z-score is negative, I need to use this page of the chart. Notice that in this picture, the shaded area is less than 50%, or less than the mean. So this page, all the z-scores are negative. Okay, so if we will go back to the previous page, you'd see that all the z-scores were positive. Okay, so that other page is what we use when our answer is over 50%. This is the page we use when our answer is under 50%. So I'm asking for a z-score, or what's the area when the z-score is negative 1.28. So like this would be my z-score. So I'd look that up on the table. I'd go down to negative 1.2 over here. and then I would go across to the 0.08. When you put that negative 1.2 together with the 0.08, you get negative 1.28. Then I go across the table and down, and where they overlap is 0.1003. So my answer would be 0.1003, which is really 10.03% if I move the decimal. But again, we usually keep it as a decimal, okay? Now, the good news is that table is stored in your calculator. So depending on which calculator you have, a TI-84 or TI-83, what we do is we go to second distributions on either calculator. So that's the blue key in the corner, and then distributions next to the clear key. And then you go to choice number 2, normal CDF. And if you're on the 84, you have to type in 2 numbers, a lower z-score and an upper z-score. So depending on which area you want, if I was doing my first problem from our examples where the z-score was 1.50 and I wanted to the left, then my lower z-score would be negative 10 and my upper z-score would be 1.50. Okay, so we use negative 10 as a really low z-score on the right, and we would use positive 10 as a really high z-score on the right. Okay, and that will get us our answer. If you're using a TI-83, you're not going to have the upper and lower prompts. All you do is type in the upper or the lower and upper z-scores separated by a comma. So this is the low z, this is the high z. Okay, so this calculator function finds the area between 2 z-scores. Okay, you could probably guess if we did normal CDF, typed in -1, +1, that'd be from a z-score of -1 to a z-score of +1. That would be 68% because that's the empirical rule. Go ahead and 1 standard deviation either side of the mean. You could probably guess if I did it from -2 to 2, that's 2 standard deviations on either side. That would be 95%, etc., etc. So this is just a way for us to find these percentages quickly. Okay, so if we did the problem we did earlier today, find the probability that z is less than 1.5, and in the table we found the answer to be this. What we would do on our calculator is go second distribution, normal CDF, and then we would type in the lower z-score, which would be -10, and the upper z-score, which would be 1.5. We keep the mean and standard deviation as 0 and 1, okay, on the 84. When you type in -10, be sure you use the negative sign, not the subtraction sign. The negative sign is on the bottom of the row of the calculator. If you use the subtraction sign, you'll get an error statement. But you can see the calculator gives us the same answer we got before, just rounded, like we rounded it on the table. But the calculator actually gives the answer to more decimal places, so it is considered more precise. But again, on any answer, it is okay to round this to 4 decimal places, just like the table had. Okay. Here's some examples of using your calculator. If I asked you to do the probability of having a z or being less than 1.46, when we do these problems, one of the things we like to do is just draw a quick sketch of the bell-shaped curve, which I did here. And then I want less than 1.46, so I put in 1.46 as my z-score, and I shade to the left of that. Okay. And then remember, when I do this, we're going to use -10 as a really low z-score. So to find the area that is shaded, I would do normal CDF -10, 1.46. Or on the 84 calculator, -10 would be my lower z-score, 1.46 would be my upper, and that gives me 0.9279. On the second example, I want to know what's the probability that z is bigger than or equal to -1.39. So I draw the bell-shaped curve. Z-score of -1.39 is to the left of the mean, so I draw it on the left-hand side. And since I want bigger than or more than that, I shade to the right. And this is where I'm going to use a positive 10 as my big z-score. So I would do normal CDF, negative 1.39, comma 10. So you always do lower z-score first, upper z-score second. And then this example is just what's the probability of having z less than or equal to 1, but bigger than or equal to negative 1. That's just the empirical rule. I want to demonstrate it. So I would do normal CDF, negative 1, comma 1. And I'd get about 68%. And remember, that's what the empirical rule would tell us. So we have to be comfortable using the calculator to find these percentages. If you're doing a problem, here's how we do it. First thing you want to do is identify the distribution, which means this only works if you have a normal distribution or normally distributed variable. So that has to be said in the question, okay? Then we like to draw a picture, fill in the mean, the standard deviation, and then the number the x value you're gonna find out about. Show the z-score calculation with the numbers plugged in. Find the probability using your calculator, and then we usually make a interpretation statement. So this number 1 says the life expectancy particular brand of light bulbs is normally distributed. As soon as they say that, that means I can draw this picture with a mean of 1,500 and a standard deviation of 75. What is the probability that a bulb will last less than 1,410 hours? So 1,410 is less than the mean, so that goes over here to the left. And I want less than that, so I'm going to shade to the left of that, which means on my calculator, I'm going to use negative 10 as my really small z-score. Then I just need to find the z-score for 1410, which I did here. It's negative 1.2. Then we do normal CDF, and again, I'm going to start with negative 10 to negative 1.2, and that gives me 0.1151. And then here's my interpretation. There is an approximately 11% chance of a light bulb lasting less than 1,410 hours. And I just turn that 0.1151 to a percentage by moving the decimal 2 places to the right. So that red statement is a context statement. We want to get used to making those statements. Like, what did we find out? Number 2, life expectancy for particular brand of light bulbs is normally distributed. Again, that lets me draw the bell-shaped curve. With a mean of 1,500 hours and a standard deviation of 75, what's probably a light bulb will last longer than 1,700? So again, 1,575 go in the middle. 1,700 is more than 1,500, so I draw that to the right. I shade to the right of that because I want longer. Then I do a z-score. So 1,700 minus 1,500 divided by 75. Remember, we always subtract the mean. That always comes second in this equation. I get 2.67. And then since I'm going to the right this time, remember, I use 10 as my really big z-score. So normal CDF, 2.67, comma 10. That gets me 0.0038, which is less than 1%. So I'd say there's less than 1% chance of a bulb lasting longer than 1,700 hours. So these light bulbs aren't going to last that long. Now my third question. This is our first time where we're going to try to find the area in between two values. So it says the life expectancy of a particular brand of light bulbs is normally distributed. Yep, I can draw the bell-shaped curve then. With a mean of 1,500 hours and standard deviation 75, same setup as that we've had. What is the probability a light bulb will last between 1,563 and 1,648 hours? So those are both above the mean, so I write them to the right. I'm going to shade in that area. Notice this time, though, I'm not going all the way to the right. We're going to go from 1,563, and we're going to stop at 1,648. So I need to find the two z-scores. So I did z1 first for 1,563. That's 0.84. And I did the z-score for 1,648. That's 1.97. And then I do normal CDF, low z-score to high z-score. So 0.84 is the lower of the two, and 1.97 is the higher. And I get a 0.1760, so about 17%. So there's an approximately 17% chance of a bulb lasting between 1,563 and 1,648 hours. So when you're doing normal distribution problems, draw a picture, write in the numbers, do the shading, okay? Then calculate your z-score, and then use your calculator to find the percentage. And then you should always make a statement, a contextual statement about what you just found, and use the terms that are in the problem. So good luck.